Well, since you are coming in, and it seems like we might have a few stragglers, but let's get started. I want to welcome everyone to today's webinar on optimizing Kubernetes for AI workloads. I'm Colleen, and I'm here with my colleague Devo from DevZero, and we're also joined by Mubin Saeed from NVIDIA. So Mubin, welcome. Could you tell our audience a little bit more about your role at NVIDIA and what your focus is on?
Yeah, I'm Mubin Sayed. I'm the Global Solution Architect Lead for AI infrastructure. The AI infrastructure, what we call as AI factories, deal with both the infrastructure, the hardware, the platform, the drivers and the frameworks that come with it, and also enablement of the services on top. So I help telcos build, create AI factories at gig scale. Telcos have been also part of a large deployment for their sovereign countries. So we have been globally involved with multiple of these telcos as what we call as NCPs, which are cloud partners, NVIDIA cloud partners, and we built and provide them guidance on reference architectures. So I also help within the telco domain. Telco is interested in using AI for their optimizations, network optimizations, and also creating a new market, which we call as inference edge. So that's where telcos are focused on as one more strategies introducing in the market.
Great, thank you for joining us. And Devo, welcome. Can you introduce yourself to the crowd?
Yes. Hello, everyone. I'm Devo. I'm the co-founder and CEO of DevZero. At DevZero, we help companies reduce their Kubernetes infrastructure costs by right-sizing the infra based on active utilization. And so we do this by analyzing the entire Kubernetes footprint at its core. And then we enable a bunch of automation to right-size both the workloads as well as the nodes and the node groups inside of those Kubernetes clusters. And so far, we have seen in between the mid-30s to about 87, 88% in a reduction of ultimate costs across the customers that we serve. And my background, I'm an engineer, and I've spent over a decade working across a variety of infrastructure platforms. Super excited to chat with Mubin here today.
That's great. Thank you, Devo. So we'll get started. And, if you have any questions from the audience during the webinar, please don't hesitate to write a comment, and we'll try to get to them at the end. If not, we'll reach out after with individual answers. But great. So, let's start, Devo, by painting a picture for our audience. When platform engineering teams do come to DevZero, what's the typical state of their GPU and even CPU infrastructure? What pain points are they experiencing that made them reach out in the first place?
Yeah, so primarily the platform eng teams that we get to work and collaborate with, they are running pretty large Kubernetes footprints. So it could be a very, very large cluster spanning thousands of nodes, or multiple clusters, each of them running tens, hundreds, or thousands of nodes. And of course, in many of these cases, these clusters are also managing hundreds to thousands of GPU devices underneath, with multiple GPU devices connected to each node from in a variety of cases. And the fundamental problem is very simple. It's over-provisioning. And over-provisioning, especially when you're interacting with GPUs in the cloud world, comes with a large amount of costs. And teams would ultimately, they want to reduce their operating expenditures just for a variety of business reasons. And so maybe I can talk about a scenario that we encountered a few weeks or a couple of months ago at this point. So team, nowadays there's a new model coming out ever so frequently. And in this case, it was DeepSeek. DeepSeek is the model that we encountered, where they had 8 replicas of this workload running in one of the clusters in production, I believe. And so using DevZero's telemetry, you're able to see that, sure, every single one of those 8 replicas, it was actually using a ton of the VRAM, which is the GPU's memory, which normally happens when the model and its relevant weights, etc., are all downloaded and loaded up, ready to serve inference requests. But when we started to actually monitor the GPU utilization, which is what happens when you actually make requests to it, we discovered the requests were only ever hitting one of the 8 replicas. So essentially, we had a models, 8 instances of the same model loaded into memory, but it wasn't really delivering very much value, although that one instance was. So in this case, what we realized was happening is in production, this team truly needed 8 replicas for a variety of reasons. But the same Helm charts, etc., these tend to get copied over for the most part. It might have shown up in an online tutorial somewhere. And so that got applied in prod. And the same thing got copied to pre-prod and to the dev environment. So you had 8, 8, 8, 24, when ultimately the team probably needed 10 or 11 instances running across all of their environments. So yeah, that's the sort of problem that we normally see people face, and that's what we help them out with.
Thank you. Moving, does this align with what you're hearing from the NVIDIA side when you talk to customers running AI workloads too?
In inference scale, that might be the case where optimizations are needed, but AI infrastructure, when telcos or the other NCPs or even the hyperscalers, when they build AI infrastructure, they're building it out for the whole complete AI journey, not just for the inference. They're doing both the data ingestion, model training, as well as the high volume inference. Now, these infrastructure obviously needs to generate tokens at more accurately and at a faster rate with three technical methodologies. AI model development, accelerated computing infrastructure, and enterprise-grade software. So all of these together will get you a good user experience. Now, with each generations of the GPUs coming in, there are very good improvements on the hardware in terms of the core count. Each GPU has a multiple of additional core counts that these workloads can efficiently take use of. That said, there is also on the inferencing side, there is the inferencing, how to optimize the inferencing methodologies that NVIDIA recommends. However, with the development environments and the do your own development or the deployment models out there, they have not, what we have seen is that they need help in optimizing these. And DevZero can definitely help in getting these optimizations. And one of them is to serve high volume inference optimally and efficiently. So in this way, what Debo is seeing is right. There is a need in the market to efficiently use the different methodologies, the technologies that NVIDIA provides, even in these development environments or in your do your own model kind of deployments, cluster deployments. And some of these GPU utilization techniques in Kubernetes, some of these use cases are in low batch inference or high performance computing, Spark-based data analytics, and visualization. So all these use cases definitely need better or more techniques that are present, that are provided by NVIDIA that can be leveraged there to enhance their efficiency.
Okay, thank you. And when you talk with enterprise customers, what are some of the main factors affecting their GPU utilization? What's driving the gas that you're seeing moving, and how are the teams addressing them?
Yes, as I said, right. So there are multiple strategies for what we call as a good put value. That's the KPI that we measure on the AI infrastructure that sees that how best you're utilizing in your environment the GPUs. The first layer that we look into is the technology stack that includes the data center architecture, the compute resources, which includes the GPU. Networking is a very critical need because of GPU to GPU communication, whether within the box, within the node, or outside with multiple nodes. Storage access to where we do checkpoint, store checkpointing, or even in now the new technologies that we have introduced with Dynamo, putting KV cache in the storage, the infrastructure management, all of these have to be efficiently deployed to run AI workloads reliably. Now, the streaming multiprocessor that I talked about, right? So the core count is high. Now those need to be efficiently used by these workloads. Otherwise, what you're leaving as the compute power of the GPU is unutilized. Um, that enables like the workloads need to take more concurrencies, more number of sessions to utilize GPUs. So with that said, I mean, all these, whether these techniques that are being used, they also need to be seen that AI workloads is something different. AI workloads can have interruptions. The job, it takes a long time. When you talk about training, it takes a long time. And so there are, for different scenarios, there could be interruptions, or they could be times where the inferencing is not, the request for the inferencing is not getting, and the requests are not coming through for those particular models, but the inference for others may come in too. So that optimizations need to be done. And that could be done by leveraging the GPU infrastructure well. There are different techniques that NVIDIA proposes in terms of concurrency management. There is technique on MIGs. So with that said, what we have seen in the market is if all these techniques are used, we see that a good close to 90% good put can be achieved with the partners like DevZero and their techniques in utilizing different frameworks within NVIDIA, that is achievable.
It's great to hear. And, Devo, when DevZero customers do first come to you, what's the gap between what they think they're using versus what's actually being utilized? Can you give us a real example of what that translates to in dollar terms, especially?
Yeah, I'll just start with a little bit of background, which I'm sure
Yeah.
many folks in the audience are already aware of. So Kubernetes, that's the area we primarily focus on, right? And in Kubernetes, there's this one interesting concept. It's called requests. A request is a way for the engineer to tell Kubernetes that, hey, this workload that I'm going to run, I think that this needs X many resources. And this could be 4 CPU cores, 16 gigs of RAM, and 4 GPU devices. And this usually doesn't necessarily have a one-to-one correlation with exactly what the software is going to use when it's running. And so the gap that we see when customers come to us, this is the bit that starts to get a little shocking. Companies think that they are running in a highly efficient manner because it looks like, yes, I might have 100 cores of capacity in my cluster, and it looks like I am requesting 90 cores. So they think we are running at 90% utilization. In reality, though, let's take a GPU example now. Just because a graph somewhere shows that the VRAM is being utilized, or that some process is running that's using a lot of memory consistently, doesn't mean that process is actually being executed. This is where having to look at things like network metrics, file system metrics, and also spikes in how a workload is performing. These are the areas where we end up seeing a lot of waste. Sure, resources might be claimed in some instances, but when we dig into the actual utilization data, we tend to see between a 15 to 25% utilization across the clusters. In many cases for the GPU world. And maybe shortly I can show a couple of screenshots that I took earlier this morning as well, where we'll see that sometimes GPU devices are actually entirely underutilized, or unutilized, I should say. You're running an H100 cluster in the cloud. You've got 50 GPUs over provision because of this replication issue that I was talking about before. Maybe Shani, if I could get the other slide for a second. But yeah, as you're doing that, I can just talk to it. So this is a case where this workload, for example, probably had two devices, as we can see in the pink line. Pink line is requested, and whenever a purple line shows up in whatever screenshots I show today, that'll be what the workload is actually utilizing. In this case, the workload went and requested two devices. Ultimately, it did come down to one device, but it never used any VRAM. So in this case, it went and told Kubernetes that, hey, I need GPUs. And Kubernetes reserved a GPU for it, or two GPUs for it, and gave it to it. But ultimately, it didn't really end up going and using any. And so very similarly, we have seen multiple other cases where we have helped customers go down from 8 devices to 4 to 2. And it's all based on active demand patterns, right? It doesn't mean that we're always going down. Sometimes we'll go from 4 to 8 to 16 as well, just based off of how requests are coming in. And as Mobeen already pointed out, our focus primarily where we have seen the most amount of impact is inference workloads. We're also doing some stuff on the training side that I'll go into later today. But this sort of stuff relates to or will equate to thousands of dollars a day, some cases tens of thousands of dollars a day. And in an annualized basis, that's hundreds of thousands or millions of dollars that we normally help companies recover. So, yeah, Colleen, please.
Thank you. No, it's great to really highlight why visibility is so critical. You can't optimize what you can't measure, but switching gears a bit, many developers start with NVIDIA SMI for checking GPU status, but enterprise grade monitoring requires more sophisticated tools. Can you walk us through the NVIDIA Data Center GPU Manager, or DCGM, and what does it show you? Why is it essential for understanding true GPU utilization at scale in Kubernetes environments like the one Debo just showed?
That's correct, Colleen. Debo has highlighted some of the usability on terms of memory, GPU utilization use cases there. So unlike CPUs, which handle a few threads, GPU handles thousands of operations at once. So this compute density will have an impact on the power draw, heat and memory systems. That could be a bottleneck. So that's what we have to be very, very careful monitoring and visualizing that. DCGM is a powerful tool designed to manage and monitor NVIDIA GPUs within the data centers, has been used by a lot of these different partners and customers. It includes active and passive diagnostics. It gives you a cluster level monitoring with native Kubernetes environments. It exports the GPU metrics that you have seen in the graph just before with real-time monitoring and alerting as well. And this you can collect this through and you make use of within your dashboards. It supports open telemetry as well. So with that said, I mean, it has a lot of these capabilities, not just to visualize better utilization of the different components within your system, but also enabling to get all these data in a meaningful manner through open standards that you can look into graphs and analyze them. So it's a very good tool that customers and partners have been using.
That's great. Debo, would you like to add anything to that?
Yeah, I think Mobeen is like so spot on this. And like GPU devices ultimately, in a variety of ways, they're slightly different from our traditional CPU devices, right? Colleen, can you mute for a second? I'm hearing a bit of feedback. Yeah, and so for CPU devices, we normally end up using cAdvisor, which is a bit of software that Google had put out into the world a few years ago. And cAdvisor gives us resource metrics on how each container, which is ultimately a Unix process, what sort of resources it's actually using. And for GPUs, NVIDIA GPUs, as Mobeen called out, we use DCGM, and we'll end up using the NVIDIA GPU operators and a variety of other telemetry that they have put out for us. And so another interesting thing I've seen is GPU compute, that computer has CPUs in it. And that computer has traditional RAM in it as well. And those are areas where we have seen quite a bit of underutilization, sometimes over 95%, where in many cases the GPUs are truly really being used. But the CPU and the RAM on those devices, for however the platform engineering team has sorted things out in the internal infrastructure, they've just said if a workload needs GPU, it goes on this computer. And if it requires CPU or RAM, it go somewhere else. And so the CPU and the RAM just stays completely unutilized in those cases. But yeah, funny example. Please go.
That's really helpful context. So once you have this DCGM data, you're looking at multiple metrics like VRAM utilization, GPU compute utilization, and others. So Devo, how do you interpret these together to make optimization decisions with there's multiple, what's the difference between a model sitting loaded in memory versus actually doing work?
Yeah, that's a solid question. Shani, if you could please share the slide one more time, just talk through it. So there's quite a few graphs over here. This is actually from our dashboard as well. But before I dive in, let me just walk through the data points that we collect. So this is data for one workload. I believe it's of type stateful set or job or something of that sort, a Kubernetes workload type. And this is the class of metrics that we tend to collect. So on the top left, we see that over 40 cores are actually being requested by this workload, and it's probably using less than 10 CPU cores. To the right of that is its network utilization on what it's sending out, what it's receiving. On the memory side of the house, similar story. The gray line over there for memory is the memory limits. The pink one is how much memory it's requesting and how much it's using. And traditionally, what we end up seeing for the most part is real utilization falls quite a lot below requests. And that's where the crux of waste ultimately comes from, right? But I'll get to that later on. To the right of that is on the file system side, you have a workload running. It's a container. It's just a process at the end of the day. And it might be reading stuff from the file system or writing to the file system. So we also track that data. And under that, we have the two core GPU metrics that we track. One is VRAM utilization, and the other is the GPU device, how much of that is being used. And so this is, again, similar example where this workload ended up using slightly more than 2 GPU devices. So you can round up and call it 3, but it ended up requesting 4 consistently. And so one of the things our recommendation would ultimately ask it to do, and by recommendation, I mean our automation optimization, it will bring it down to 3, just to save on that 1 GPU device. And in order to come to that recommendation, you'll actually see similar things happen both on the CPU side of the house as well as the memory side. We are taking all of these metrics into account on how the workload is performing, what other workloads are talking to it, what workloads this workload will actually talk to. And based off of that, we make a recommendation decision. So in the DeepSeek example I talked about earlier, very similar picture, right? So you're running 8 replicas, and it looks like only one, sure, VRAM is used equivalently across the board for all 8 replicas because the model is loaded. But when you actually look at the GPU utilization, you see less than 1 device is being used. Less than 1, we round up to 1. And that's how you know, okay, the other 7 can probably be freed up potentially for other workloads to essentially go and use those. And this is an area where the telemetry that we get from DCGM, and as Mubin rightfully called out, it's ultimately a lot of open telemetry metrics that NVIDIA has a lot of utilities and tooling that it exposes. And this is super invaluable. And this is where looking at it as a snapshot of what happened at 9 a.m. This morning, like that is not good enough. So we need to look at these metrics over time, understand the patterns. If it's an inference service, might be getting hit during business hours, depending on the class of environment that it's running in, or it could be a training job of some sort, or a cron job of some sort that runs on a certain day of the week or a certain day of the month, etc. The historical confidence that we have, the historical context, like that's ultimately what gives us the confidence when we make these automation decisions or optimization decisions. And so we look at VRAM, we look at the compute utilization, We'll look at network, file system, etc. Low VRAM usage usually means that I might be able to move this workload over to a smaller GPU. In some cases, when we see VRAM actually being capped off, we'll recommend moving to a bigger GPU as well. So that's how we have been approaching this problem.
Thanks, Devo. And from the NVIDIA tooling perspective, are there other metrics from DCGM that teams should be paying attention to optimize further?
Yes, so what Debo has highlighted are specific VRAM and GPU utilization, but at the same time, the graph that we saw just now talked about the network, talked about the file system within this, how it interacts for the inference request. So that said, as I said, there are other diagnostics that you need to do. There are other variables that will prevent your request from performing well. Those could be on the power bandwidth hardware. There could be uncorrectable GPU memories, errors, persistent compute errors, or NVLink or PCI interconnect errors. Those need to be monitored very well and they might introduce large compute latencies or dropped connections, usually low compute or bandwidth, memory bandwidth. So, anyways, the whole idea of any AI infrastructure is to remove the weakest link, whether that weakest link comes in the memories, whether it comes in the compute side, or whether it comes under the network. So what we want is an AI infrastructure that has very fast network that can support very high bandwidth data rates, very fast and large memory footprint, especially when we are doing model sizes that are large, and also memory bandwidth. So all of these are important that needs to be looked into. We have to remove those weakest links in order to optimize and create a very good value. So all these are the techniques that you need to see, and all of these variables count. Those diagnostic, in addition to whether or not the VRAM is better used within these requests, the inference requests.
Thanks, Mubin. So now we've talked about having the visibility. I'd like to go into how we can act on it. So previously, Devo, you mentioned how scaling down from 8 replicas to 2 based on actual usage patterns can help. Walk us through that decision-making process. What signals tell you it's safe to scale down, and how do you avoid disrupting production workloads?
Shani, if I could request you to share the slide again. Just going to go to this one. So there's a couple of things that are very important over here. Most workloads at the end of the day, they're very stochastic in nature. Like when a user is going to show up on a website and do a certain thing, that's when a certain code path will end up calling either an inference API or something of that sort. It's a lot of if. And so given the stochastic nature of workloads, we can't just blindly go from 8 to 2 or 8 to 1. Like that's not going to work. So we look at it in a couple of different ways. And we have a certain policy language that we use at DevZero in order to direct our optimization practices. That is good for aggressive, even a very, very aggressive stance. When we see that, sure, something requests 8, let's say 8 GPUs or 8 CPU cores or whatever, and it's actually using 1, we'll actually never go from 8 to 1. We'll probably go from 8 to 4 first. We'll see how the workload is performing. And this is where the other data points, like the network utilization, the file system, like those things start to become very important. Is the workload still is something else starting to throttle the workload at this point in time? In which case, as soon as we see any of those errors or throttle conditions starting to happen, we'll just scale it back up again. If it does not happen, we'll continue to scale it down slowly. And we take there are cases when we can get very drastic for a very, very aggressive policy, but normally we'll just take step decisions keep monitoring for a certain period of time, and then we'll make the next optimization decision. But key over here is constant monitoring. Like, again, as I said before, we collect all of these data points for every single workload every few seconds. I think it's usually 1 to 2 seconds, or in some cases, 10 seconds is usually one of the highest that we go to. This is production. Now, in many lower environments, so your dev, staging, pre-production, etc., those are cases where our policies, we see platform engineering teams configure them to be significantly more aggressive because the blast radius of being wrong, it's much smaller. You'll probably impact a few engineers on the team, and ultimately, there's more room to mess around. Ultimately, and so again, to sum it all up, CPU, GPU, regardless of what it is, we always monitor resources very, very, very frequently. And then right sizing is always based on these policies where we have a certain set of predefined buffers where you can configure how concepts like hysteresis start to get implemented, where after making an optimization decision, wait for 30 minutes, see how everything settles down before you ever go and try to do something else, or wait for a day. So that's where our policy language essentially helps us maintain a high amount of reliability while we help teams get to a significantly higher deal of cost efficiency. Colleagues.
Thanks. And you also use checkpointing as another optimization strategy, right? And I know the traditional use case for checkpointing is really disaster recovery, but you're using it for cost optimization. Can you explain how CUDA Checkpoint enables you to move workloads around without restarting from scratch? And when does this strategy make the most sense?
Yeah, and maybe I'll say a few words, and then I'd love to hear from Mubin on this topic as well. So checkpointing, as you called out, Colleen, it's been around for a minute. Primarily, disaster recovery has been the main reason why we've had checkpointing. So a computer goes away, how can we get the processes back in some way, shape, or form, or at least maintain the file system state so we don't lose all of our data? We use it for a slightly different purpose. Our goal is we care about running efficient infrastructure. That's it. It just happens to save our companies a lot of money as well. I have a training job. It'll take me a week to run. It'll take me 2 weeks to run, whatever. Now, I have run it on some computer. Let's say I'm running it on a spot instance. And spot instance, the concept is they're very preemptible. That's why most cloud providers, NCPs, etc., they sell them at very, very discounted rates. But the caveat is those computers can get taken away at any time. So 2-week job. I'm 5 days in. Computer goes away. What happens? Traditionally in the world today, we have to restart. So we have just lost 5 days of progress. And this is where with checkpointing, what we are able to do is we store process state. Everything is a container at the end of the day in our Kubernetes land for the most part. And so for that container, we'll store its file system. We'll store its RAM. We store its existing TCP connection. It's a bunch of metadata that we essentially end up persisting. We'll also store the relevant GPU state that it was holding at that point in time. And we freeze it and we move it to a different computer. So when we are doing our traditional optimization work, Kubernetes has this habit of restarting workloads all the time. And restarting is not good for some classes of workloads, especially ones that take 14 days to run. If I restart something on day 13, like it's a disaster. So this is where we'll freeze process state, change its requests or whatever else, just to make it a little bit more efficient, move it to a different computer or the same computer. Either way is fine. Yeah, and this is where I'd love to get Mubin's thoughts on this. Like CUDA Checkpoint is something that's been really nice.
Yeah, Mubin, thank you for that, Devo. Mubin, could you share more about how CUDA Checkpoint works?
Yeah, so NVIDIA CUDA Checkpoint, another tool that transparently checkpoints and restores CUDA state within a running Linux process. It works together with the open source CRIU, checkpoint restore in user space utility. So a per process checkpoint can be used in combination with containers to checkpoint the state of a very complex application. What we normally do, use cases are fault tolerance with periodic checkpoints, preemption for lower priority work on a single node, which I believe DevZero uses it, and cluster scheduling migrations. So all these techniques, I think you guys have well used it. The CUDA checkpoint, what it does binary is it toggles the state of the CUDA process from suspended to running. So typically, when in this process, there are multiple processes, these multiple states. I'll just highlight one such state from suspend to running. So if I'm suspending it, any CUDA driver APIs that launch work, they will our managed resources or impact the GPU state are locked. So that's the first step. You lock it. Then already submitted CUDA work, including the streaming callbacks, those are completed. So lock, then the existing processes at work that's been already been asked for, that's completed. The device memory is copied over to the host. And then finally, all the GPU resources are released. So this is the process where I am changing the state from suspended to running. So the other processes too that work from different states. So CUDA checkpointer for a on the performance wise, what's the overhead? They will talk about the overhead. So if you're using this frequently, then you definitely introduce the overhead. The overhead is proportional to the data size that you're checkpointing. Right? So if you go from 100 megabytes to around 1 gig, it's a linear increase in the overhead. But this linear overhead is a very good trade-off, as Deborah pointed out. You guys are using it, right? So, in terms of better utilization, good put values, if you're trading off with that, then this is a very good technique that can be used.
Thanks for adding some more color to that. We'd also like to talk about another NVIDIA technology for improving utilization. It's multi-instance GPU or MIG. Mubin, can you dig into that, explain what MIG is and when it makes sense to use it?
Yeah, so I think there is a slide that was initial. So if you can put that on, there are different concurrency techniques that NVIDIA proposes in order to better utilize your GPU resources. And those are depending on the user, the customer requirements. We have the multi-process CUDA, where you can have multiple processes working within the CUDA. At the same time, we have time slicing, where different workloads can based on the time slicing, use the resources. There is a MIG that you guys have really used in your environment, which will give you a very complete hardware isolated for different components within the system in the GPUs, whether it is accessing the GPU memory, that is all the different engines that exist within the GPU. So another is the virtualization technique, where you can virtualize the GPUs into different segments as well. So that said, let me concentrate on MIG that you guys have used in your environments, in your platform. This multi-instance GPU is a partition. It could be, depending on the GPU type, it could be different partitions. What it gives you is an isolated instance with dedicated compute and memory resource. So if somebody is very, very security conscious, then this hardware isolation will work with this strategy. This MIG technique will work. So within MIG, each instance process has separate and isolated paths to the memory system, to the ports, the on-chip crossbar ports, to the L2 cache banks, the memory controllers, and the DRAM address buses. So all of these you will get as a complete environment for yourself, for any workloads to make use of it. So these compute resources, depending on the GPU types, you can have a very good GPU memory. If you're looking for Blackwell series of GPUs, then these are come with the partitions also come with sufficient sizes, GPU memory sizes that you can use, and so this is a very good technique. The MIG is a very good technique to better utilize a GPU, a single GPU that has a large memory footprint, which your workload doesn't need. Your workload may just need a fraction of that. And so these fractions, these hardware isolated fractions, are a good technique for a good utilization, good put values for the inferencing.
Thank you. And Devil, what else are you hearing when it comes to MIG?
Yeah, so as Mobeen was saying, right, we have the technology to leverage MIG. We actually partnered a lot with NVIDIA last year, just to make sure we understood MIG deeply enough, how exactly it was doing the hardware level isolation, specifically around memory, so that there's essentially no shared memory ever. And generally, I think like it obviously has really promising potential to solve the GPU shortage challenges that we continue to face. So for us, in our world, often we are dealing with really low-hanging fruit. The examples I cited today, I have requested 8 devices. I need 1, I need 2, I need 6. So we just free up devices for the most part for customers. It goes back to the cloud. It helps them save money. In most of our customers, what I find is the models are large. The models just keep getting larger over time, is what we have at least experienced. And at that point in time, it'll end up using most of the VRAM that's available to it. But at the same time, we are also starting to work with a lot of customers that now manage their own infrastructure. They have their own data centers, or they are in some colo where they have a lot of GPUs that the platform teams are managing themselves. And this is where, like in the cloud, H100 is too big, get rid of it, get a new E100. When you own the hardware, that's not as easy to do. And so this is where we have already started to chat with a few folks about like MIG, being able to like partition the whatever VRAM that they have available so that they can ultimately get to a higher utilization rate. So yeah, short answer is I totally agree with what Mopin said. We're starting to see quite a bit of that as well, especially in our on-prem customers.
Thanks, Devil. Mobeen, let's zoom out a bit to the broader infrastructure picture. When you're building high-performance AI infrastructure, what role does networking play? And how do some of NVIDIA's newer technologies fit into an optimization strategy there?
Definitely, it is critical, especially when you are looking at DeepSeek or large model sizes, Llama kind of 400 about billion. It maxes out the VRAM, as Deborah pointed out, right, for a single GPU. Then you have to use different techniques. Parallelism is one of the techniques that you use, even in inferencing. So those require multiple GPUs. In fact, multiple nodes. Now, just on the training, definitely you need large clusters of GPUs, 1,000 and above, just to train. Fine tuning also requires sufficient sizes of GPUs, but for inference, also what we have seen is that you are using a lot of these GPUs, especially for scaling. So when you scale to high volume inference and when you are addressing multiple model sizes, networking plays an important critical role, not just for training, but also high volume inference. That's what we have seen. And that's what we have positioned the market in, and the market now realizes even for inferencing that you need not just you need a scale-up architecture as well. What I mean scale-up architecture is a collection of GPUs that gives you a unified memory, large footprint memory that can, this large footprint can be efficiently utilized in the hardware for a good book value for inferencing as well as other workloads, training workloads. So there is parallelism involved even in inferencing, That includes the networking. Fast networking is needed for interconnect GPU to GPU communications. So that's where we are. But also, what we have introduced now different techniques within inferencing. One of it is the disaggregated. What we are positioning now is because we have the scale up architecture, we have a good memory footprint and a huge GPU capacity within. Different aspects of inferencing can now be used. The prefill, the first token actually is a compute intensive task. That's where the GPUs are mostly utilized. But the next tokens, the next tokens require more memory. It requires us to save KV cache, and so it is computer intensive as well, but it is predominantly memory intensive technique. So we have disaggregated this in the inference and used different GPUs for different tasks within the inferencing. And also on the KV cache, the optimization now has been because GPU memory is fixed, and that's being used for compute and calculating the next tokens. The previously calculated tokens can reside in other storage mechanisms, whether it is on the host side, on the external storage, depending on, or in the CPU, depending on where it makes sense, how we optimize. So inbuilt, these techniques, what we call NVIDIA Dynamo, has all these feature sets that's fully automated for you guys that you can leverage. Finally, because there is a huge data transfer between the memory and between different storage mechanisms, between GPUs to GPUs, we have introduced what we call NIXL, which is the NVIDIA Inference Transfer Library. That's a communication library that provides a very high throughput, latency point-to-point communication library and provides very consistent data movement API for you guys to leverage and use even for high volume inferencing.
Thanks, Mubin. And since DevZero is operating at the Kubernetes layer, how much do you need to think about these lower level infrastructure concerns?
A little bit. So our majority of our customers that are interacting with GPUs, they will run inference workloads either for end user traffic or for fine tuning and whatnot. And in some cases, a lot of batch inference jobs as well. And so for these workloads, our interface of interacting with infrastructure is the Kubernetes layer. And we can be fairly agnostic to what's going on underneath, thanks to all of the other NVIDIA tooling with DCGM, etc., that we've already talked about today. And the majority of our customers are also in the cloud, right? So AWS, Azure, GCP, Oracle Cloud. And those providers usually do a pretty good job at handling the networking layer, inter-GPU communication, etc. And so thanks to the Kubernetes abstraction that we get to work with, we can sometimes be pretty insulated from the underlying challenges. But as Mubin mentioned about KV, NIXL, etc., like every token that comes after the first one, there is a cost. Like none of this is free, and compute goes into memory after a certain point in time. And this is where inference being this heavily memory focused, like you load your model and you start to serve real life traffic. And that starts to become a constraint at a given point in time because there's only so much GPU memory that's on a card or on that node that's available. And so offloading some of these parts of the inference pipeline, we are seeing some of our customers at least start to talk about it now as the next optimization vector, because unfortunately, you still can't download more GPU memory from the internet and just have it be available. So, but yeah, at the end of the day, our core focus is still, we see a lot of low-hanging fruit out there. We have people that are allocating GPUs and not enough is still getting squeezed out of them. So we are focused primarily on that in the near term.
Thanks, Devo. This has been a great discussion. We are getting a little close to time, and I want to make sure we can make these insights actionable for our audience. So let's kind of just move on to what, how they can get started tomorrow. If, if someone on this call manages Kubernetes cluster with GPU workloads and they want to get started this week, what are the first 3 steps they should take? From the
Yeah,
NVIDIA.
in brief, what I would say is in order for your cluster to be highly optimized, number one thing that you need to do, there are 3 things you need to do. But the very first thing that you need to do is start with the high performance, hardware optimized for the use cases and the workloads that you have, the AI workloads, especially on the AI workloads. Traditional workloads are way different from AI workloads that need to be understood. So the hardware plays an important role there in the infrastructure. It's not just a single component, all the components to remove the weakest link, as I said. Then identify, when you're operating this, identify and remediate any interruptions, any unused capacities proactively. You monitor that, which you guys have been effectively doing that. And then finally, leverage the different NVIDIA frameworks, different techniques, the different for specific domain use cases as well, and also different strategies to ensure that the GPU is fully utilized. There are, as I mentioned, the 4 techniques there in concurrency, using the GPUs efficiently. So please utilize that. That will enable you to serve your Kubernetes workloads well.
Thanks, Mubin. And Devo, from the DevZero perspective, what would you add there?
Yeah, maybe Shani, if you can please share that one slide I have. So ultimately, start with DCGM. If you don't have that in today, start. Start yesterday. Get quite a few days worth of data, ideally a week, more than a week. Look for patterns. Do not spot check. Do not make arbitrary assumptions. Look at the data. The second thing I would say is auditing. The same things that apply in a production environment don't apply in all of the other environments. So no sacred cats. Audit the lower environments, dev, staging, pre-prod. These are areas where we often see a lot of waste essentially happening, a lot of like over provisioning from people just copying over production configurations. And just look for the easiest wins, right? Like concepts of a horizontal autoscaler have existed for a long time. Reduce replica counts where it's applicable. The risk for some of those things can be pretty low and the rewards are very high. So those are some areas I tend to focus on. And then look for workloads that have a very, very clear over provision stance. And like the graph that, or the 4 charts that we have over here, this is actually data coming out of a node. Like so far, I've tended to focus more on individual workloads. So this is what we were looking at before, but I'll just talk about nodes now. So look at this stuff, see what cases where a lot of requests are being made, but not enough is being utilized. Like the 2 purple lines at the in the 2 lower charts, that's actually a pretty good case. Like in this instance, whatever this team is, they have been using close to the total number of devices available on this node, which is I think 8 devices. And it's also using the GPU memory pretty effectively in the last little bit over here. So monitor, find cases where workloads on nodes are clearly over provisioned and start to make incremental changes, monitor impact, make more changes. And especially if you're running in the cloud or essentially renting capacity in any way, ask your providers about preemptible instances. Amazon calls it spot. Many clouds call it spot. Some providers call it preemptible. This is essentially spare capacity that you can get at a significantly lower price. And this can be very helpful for the non-production environments, especially. So, good.
Great. Perfect. So just about at the hour, and I know there's a lot more to discuss, but I want to be respectful of everyone's time. For those of you that did submit questions, we'll make sure to reach out individually with answers. But, please don't hesitate to reach out to either DevZero or NVIDIA in the meantime. This has really been a fantastic conversation. I want to thank Mubin for joining us, and of course, Debo, and thank you for everyone that attended. If you want to see where your clusters stand, check out DevZero's free trial and NVIDIA's tools, and we'll send that information, the link to that recording and some other helpful information after. But thank you all again. Really appreciate it. Enjoy the rest of your Thursdays.
Thank you. Thanks for having me.
Thank you.
Bye.
Thanks so much, Mubin.
Thank you guys.